Now let's talk about short pulses on transmission lines. Oh, I love a new marker. Okay. Short pulses on transmission lines. So everything that we've studied up until this point has been essentially DC switched pulses. We've looked at a leading edge that was turned onto a DC value, and then we've waited until that has shaken out of the system. And we saw that we had some effects like ringing, latency, and the general things that are caused by reflections. Now we're going to look at what happens when the discharge happens fairly shortly after the initial charge. And that's the scenario we're going to look like. And this will actually be a fairly simple exercise because honestly, if you understand the DC stuff, the other stuff is really a cakewalk. And I'm going to switch over shortly to a couple of PowerPoint slides to actually just show some computer outputs of what happens when you put short pulses through a transmission line. The theory, you've all mastered it already. If you've got a transmission line, and when we talk about short pulses, what we really mean is a pulse that typically has a duration of less than a transit time. So for example, if I've got my R sub s source, and I've got some sort of function of time that we put into here. Here I've got a load resistance and an intrinsic impedance Z0. A distance which is related to the velocity of propagation times the transit time. So if I pick a waveform, there's actually a lot of different things that we use to send pulses. The simplest one that we'll work through quite a bit in this class are just little square pulses. They could represent a digital 1 or a 0 or some higher order modulation where you're using different discrete levels of the pulse amplitude to represent combinations of 1s and 0s. So let's say, for the sake of argument, let's start off. Let's say that we're sending a pulse. We'll call it T sub B for a bit. It'll have a bit period of T sub B in time and a voltage level of, V0, say. Well, I don't even really need to draw equations for this, do I? You know exactly how this thing is going to travel on this wave, on this transmission line. As soon as the switch closes and we actually generate this waveform, that pulse is going to move down with constant velocity. It's going to get to the end, and what's going to happen? I'm going to get a reflection, gamma sub L times V0 in the backwards direction. And then I'm going to get a transmission, 1 plus gamma sub L, over into the load resistor. And of course, if this is mismatched, it's going to reflect off here, transmit, reflect off here, transmit. And we're going to have this same ping pong game that we had in the DC analysis. The only real difference, and this is the one thing you have to worry about when you're actually working these problems, is that unlike the DC case where a DC source switched in and stayed switched in, the only voltage you see in the short pulse at the load or the generator side or source side is the pulse that's immediately hitting that junction. You don't accumulate voltage like you do in the DC case. Remember, in the DC case, we set the waveform down there and we tracked reflections, and whatever we tracked as a reflection, we had to add what was already there. All the previous reflections or waveforms that had struck the load, because they were continually being fed by the source. For pulse problems, you do the exact same analysis. You just got to take care that you don't keep adding it up. I've seen that's a common mistake where people will add it up to all the other pulses that hit the end of the line. So, well, wait a second, they're not even there anymore. That was in the past. So that's conceptually the idea. And what's more, it doesn't have to be a square wave. You can make any kind of pulse and explore that waveform. For example, if this was a triangle. Well, keep in mind, the only thing that you have to worry about when you do non-square pulses or non-DC pulses is that there's sort of a chirality to the problem, whether you flip it right or left. When you look at the time domain, I've got a waveform that starts at 0 volts, jumps up to a value, and then decays linearly until it gets back down to 0. When I put that on the line and it starts traveling down in this direction, I actually have to make it backwards. The forwards propagating wave travels this way. And so the leading edge, which I've drawn in the time plot this way, has to be placed on the other side in my distance, in my graph of voltage versus space. Do you understand that distinction? This is voltage versus time, the earliest waveform, the later part of the waveform. This is voltage versus space. So it's going to go down, it's going to strike the end of the line, and the backwards propagating waveform is going to have that leading edge that looks like this. But this is voltage as a function of space. It's going to travel down this way. Strike, reflect, come back here, reflect and transmit, come back here, reflect and transmit, and overall die down. Now, any questions before we look at some graphs? Yeah, go ahead.
The signal doesn't remain the same.
That's right. Well, the thing is, these lossless transmission lines are nice because the shape of the pulse is preserved. There's no amplitude distorting attribute on the line itself. The only thing that changes is that at the abrupt interfaces we have reflection coefficients, and a portion of all of that pulse will reflect, and a portion of all of that pulse with the same shape will transmit. And so you'll find each reflection dies off, gets smaller and smaller, and after so many transit times you probably ignore anything left on the line. But the shape will always be the same. Yeah?
Do you have to worry about, like, if it's, say the transmission time of the line is big T, and then do you have to worry about big T plus the half, basically what half of the triangle wave is being reflected and the other half.
Oh, yeah. So what happens when you're looking at like time equal to capital T plus a little bit, right? So that at the end of the line, you've got this waveform kind of transmitting here, and then a reflected waveform starting to travel back down the line, right? And the answer to that is actually if you're consistent with your reflection coefficients and your transmission coefficients, everything works out. So the amplitude, if we call this point here, if this is, say, my V plus is the voltage from here to here, the voltage from here to here is actually V minus, and it turns out V minus will be equal to gamma sub L times V plus. And the total voltage, that voltage plus that voltage, will be 1 plus gamma sub L V plus. And that's what I see in total on the outside of the line. And so the way it works out is that if you were to animate it and ignore what's coming out of here, a perfectly formed 1 plus gamma sub L pulse will come out of the line. If you ignore what's going on over here, a perfect gamma sub L pulse will emerge out of that junction, and a perfect pulse will be absorbed by that junction. And it turns out that the boundary, all of the voltages will match up, so that total load voltage on either side of the junction of the transmission line will always be the same. It takes like an animation to really kind of drive it home. You can maybe play around with some of the pulse. I think I have a couple pulse animations on the website that you can look at and kind of gauge what's going on. good visualization question. Okay, so let me go ahead and switch now to view graphs. I'm going to bring down the screen and fire up the projector here. Okay, our projector is warming up. 3, 2, 1, 0. Blast off! Hey, there we go. So here's the scenario that we're going to take a look at. In fact, let me douse this extra light too, see if that makes the thing turn out a little bit better. We've got a transmission line. I'm going to have a source side reflection coefficient and a load side reflection coefficient. In this example, that's all that I'm going to tell you. I'm not going to tell you all the guts that are connected to either end, but we're going to put a function f of t in as a forward propagating waveform, and we're going to look at the short pulse as it bounces back. And really what I've got graphed here is what the output load voltage looks like in time. And we'll trace that out. So let me go to the next slide. Our impulse response. One of the pulses that you can put on a transmission line is, of course, a very narrow impulse, like one of those Dirac impulses you probably learned about in 2025. You learned about that in there, right? So here's the graph of that, the input. 0 everywhere, infinite at 0, and infinite in such a way that if you integrated across it, you would get a unit value of 1. That's the mathematical definition of a Dirac impulse. If you integrate it from minus infinity to t, you get the unit step function. So it's really the derivative of the unit step function. So what happens if you put that on a transmission line? I mean, there are some very broadband pulses that you can approximate as a Dirac impulse. And if you send that down on the line, what will happen is that you will trace out the amount of the reflected amplitude. So you see each of these is a Dirac impulse. Not surprisingly, each of these is a transit time, actually 2 transit times apart. So we have the first strike on the line, another transit time to get back to the source, back to the load. The second strike, another transit time to get back to the source, reflect back to the load, the third strike, and so forth and so on. In this case, our reflection coefficients are 0.9 at the load and minus 0.74 at the source. So we got a pretty badly mismatched line. This would be typical of a carelessly connected pair of logic circuits. So look at that. It looks a little different than the ringing we've been seeing in the DC circuit case. But tracing out an impulse response is actually a pretty useful exercise, right? And so if I have an impulse response, what does that enable me to do? Think back to your signal. The next few minutes, this is going to turn into a signal processing class. If I know the impulse response, then I can take any shaped pulse and figure out what the output is of this linear system. This is a linear time invariant system. If I want to put a Gaussian pulse on the input, how do I figure out what the transmission line output will look like? What do I got to do? I got to take my impulse response and my Gaussian pulse and do what with them? Starts with C. Convolve them. That's right. I know that, boy, did y'all do convolutions already? Yeah, I'm not going to ask you to do any more convolutions. The whole reason why we introduce convolutions is to make sure that you never do it again. Right? No, seriously. Like it's a very important concept. You got to fold this waveform into your impulse response to figure out what your output is. But nobody ever does that. We teach you what a pain in the ass it is in 2025. And then we teach you this trick. This trick is, you say, if you can make a Fourier transform, convolution becomes what? Multiplication. Oh, that's so much easier than convolution. If your system is linear and time invariant, always keep that in mind, because there are a lot of systems out there that are nonlinear and time varying. And then you just take all that beautiful theory of convolution and Fourier transforms and you ball it up and throw it into the sun because it's worthless. So anyway, let's go ahead and convolve various pulses of various lengths in time with this impulse response and see what happens. And we'll do this in the context of how does it distort our data signal. So I'm going to give you a pulse, and then I'm going to represent a bunch of ones and zeros. This could be the pulse on an Ethernet cable, for example, a really long Ethernet cable that has mismatches, as Ethernet cables are often wont to do. So let's take a look. First, I'm going to use a wide pulse. Here, my bit period is something like, I don't know, looks to be about 0.25 times 2.5 times 10 to the 6th, so about 2.5 microseconds. That would correspond to a bit rate of like 400 kilobits per second. Not exactly a barn burner by today's standards, but I've got a 01101110100 coming through that line. How do I use transmission line theory to calculate the effects of these short pulses? Well, I take my reflection analysis, I trace out the impulse response like I did in the previous graph, and then I convolve them. Or I actually take the Fourier transforms and multiply them together and then inverse Fourier transform them. And this is what happens. So now you can see the size of the pulse is actually much larger than a transit time in this scenario. Look at that. I get ringing on the front side, where I get the huge jump up and then jump down, jump up, jump down, oscillating, decaying behavior, and then finally it settles into a nice DC value. So if you kind of like take this chunk right here, this looks like the DC problem that we've been studying all along. We could use our DC analysis for this. You say, oh, we're connecting a 5 volt or 6 volt source, 5 volt source for a long time. And then we go study the discharge problem, when you connect the 0 volt source to it and make that change. Now, how would this affect this particular data stream? The answer is not that much. How would you get rid of this? There are a lot of different ways to get rid of this. How would you get rid of this? You would want to use a filter. What kind of filter? No, opposite. Low pass filter. See, look at this. This is going, this is very fast changes. High frequency content. This square wave, it's got a sharp transition, but for the most part, it's a really low frequency signal. So you put this signal through a low pass filter, what will happen is this high frequency stuff will it'll be stopped. It won't even pass through. The only thing you might do is just round the corners a little bit. Introduce a little Gibbs phenomena on the edges. Not that big of a deal. The other thing you could do is just try to threshold decode this. Don't even filter it. Use a nonlinear operation like a threshold decoder. Say, oh, my logic level 1s are 5 volts. My logic level 0 is 0 volts. Let's just say 2.4 or 2.5 volts is in the middle. Anything above is a 1. Anything below is a 0. So there are threshold electronics that do that nonlinear operation. And if you did that, look at this. You perfectly reconstruct your signal without all that ringing. So it might look aesthetically bad on your oscilloscope, but ringing at that scale of time frame isn't a big deal. Now let's shorten the pulse up. Now we're looking at pulses that are less than 1 microsecond. And you can see that the ringing occurs now at a scale that kind of distorts things. I'm getting ringing that occurs all the way to the end of my first pulse here. So here's for example 1 bit, and I've got to jump up, jump down, jump up, jump down, jump up, and it's still not shaking down until when you make the next state change in that scenario. So echoes from this pulse are leaking into this next pulse. We have a special word for that in electrical engineering. We call it ISI, intersymbol interference. When digital pulses are leaking into their next neighboring pulse slots, and therefore they're causing distortion. Now let's go ahead and run this through a detector a straight up thresholder. And you can see that there are points within a pulse, when I had a high pulse, that actually go below the threshold because of intersymbol interference. And there was a brief period of time when I dropped below, and I think I've got a 0 on my hands. Same with over here. So just running this signal through a straight up threshold detector does not reconstruct the perfect digital sequence we sent. What I would probably do is run this through a low pass filter and then do a threshold operation. Low pass filter to get rid of some of the ringing, and then hopefully that'll get rid of some of that intersymbol interference, and it won't push my total signal below the threshold when I have a 1, or above the threshold when I have a 0. Now, that's a simple way to deal with the problem. It gets worse, though, when you start to look at symbols that are very small with respect to time. This is in the pulses that are in the tens or hundreds of nanoseconds. Pretty high data rate. This is the tens of megabits per second type data frame. And look at what the convolution of this digital sequence is with that exact same impulse response. I can't even recognize anything. It's going all over the place. And in fact, and literally the echoes, even one echo on this line is jumping into another time slot. So that's actually the decoded signal with the threshold decoder. Notice it looks nothing like the original signal that we sent. It kind of looks like it up front here, but then it just starts to oscillate as all that intersymbol interference distorts the decoding. We would need some really serious signal processing and waveform design in order to get that channel to work as a proper data channel. Any questions so far? So here are our takeaways. Very low bandwidth signals, you can ignore the transmission line effects. Higher bandwidth signals, you have to either resort to some filtering or equalization or some really clever waveform design. And one example that I'd like to talk about briefly, I'll go ahead and raise the screen because I'm done with it, is digital subscriber line. It was a trick using transmission line theory to get more stuff on your telephone line and thereby reap a lot of profit by the phone company. Right? Because think about it. In the old days, you had this, almost everybody had this line going into their house. It was basically a pair of copper wires that acted like a transmission line. And they'd go out to the relay on your street side curb and get put in this jacketed bundle of cables that would go all the way to your phone company with various relay hops. And of course, there were mismatches along the way and lots of echoes. It wasn't a big deal because you were using voice. What's the highest frequency content of the human voice that you can hear? Yeah, 20 kilo. It depends on who you're talking to, right? The audio files would probably be like 50 kilohertz, and then 20 kilohertz is a pretty reasonable number. The older we get, the lower that cutoff frequency gets. But compared to the signals that I showed on the board there, we're talking orders of magnitude slower. And so if you convolve that analog signal with those impulse response echoes. Well, those impulse response echoes at that time frame looked like they're almost all next to each other. So it's almost like one effective impulse response. And so you can transmit the low bandwidth voice signal, analog voice signal, or even its digitized counterpart with relative ease on a pair of twisted pair cables that the telephone company uses. However, there was this big surge in interest in the internet in the late 90s. People wanted to get internet service. They were tired of using dial-up because that was slow. How many people remember actually dial-up? Are you all old enough to remember? Okay, good. I might hang up teaching the day that nobody raises their hand for that, because that was an integral part of my life growing up, dial-up connections. So how do you do broadband? And the thing is that, like, the cable company or the phone company already had this extremely valuable asset, all this copper wire to people's homes, and they just needed to find a way to take advantage of that asset. And so how did they do it? Well, they had to hide a data signal on it. They had to do it in such a way that it wouldn't disrupt your voice, and all of those reflections at the transmission line wouldn't disturb it. So if you look at the Fourier transform of what's going on your telephone wires, there's still a portion down here that's reserved for voice at the low frequencies. And then there's a part up here that you don't listen to on your voice receiver. It'll go up to past a megahertz in some cases. But this is a lot of frequency. And this signal is used for data. Usually there's a downlink, uplink portion where you can send something from your computer up to the phone company here. And then a larger portion that's used for downlink, because you tend to consume a lot more data than you produce or send up, right? And the question is, they had to come up with a way that would take advantage of that spectrum, but also be resistant to the detrimental effects of transmission lines. Because remember, in the time domain, if you have an impulse, what's the Fourier transform of an impulse? What's the spectral property of an impulse? It's flat. The magnitude is flat. If you take the Fourier transform of a delta function, that Fourier transform pair is just a constant 1. In fact, you can shift it in time. You can make it have a delay. And the Fourier transform of that is what? It's basically exp to the minus j 2 pi tau f. Right? Magnitude 1, so it's still constant amplitude in the frequency domain, but there's just this kind of complex phase taper which really just translates into a delay. If you convolve your signal with this, you'll get the exact same signal out. If you convolve your signal with this, you get the exact same signal out with a delay. No big deal. It's when both of them show up in the same impulse response that you have problems. Because 1 plus this complex exponential is not constant in amplitude. Sometimes they constructively interfere. When this is kind of real, it'll constructively interfere with this. When this is real and negative, it'll destructively interfere with this. So if you look at the frequency, the channel that this signal would go through, you would see something kind of like this. You'd have peaks and nulls based on whatever your impulse response on your transmission line looked like. Peaks and nulls. Now, your voice would be so small that you wouldn't get to the first null yet. That would be the hope. And that's why you used that kind of transmission line, which wasn't particularly good or well matched for anything when you first deployed your telephone system. But you want to take advantage of the fact that you've got this extra bandwidth, but there are some bad spots. There are some bad spots. And the way that they do this is actually quite interesting. You take, instead of transmitting a signal, a single high-speed signal up here that would be distorted, kind of like the one that I showed you in the graphs, you do a bunch of really slow signals, and you modulate them on different carriers. There are actually several different schemes for implementing DSL, but this is one of the most common ones. You take a slow signal, which doesn't have a lot of spectrum, and you put it there in frequency. You take another slow signal and put it right there, right next to it. And then another one, and then another one, and then another one. So the individual slow signal, we know that slow signals don't experience much distortion on those transmission lines. You might ring them in the front, but you can use low-pass filtering to get rid of that. And so all of these will be easy to individually demodulate. Occasionally one of them is going to be in a null. And you just either turn that one off or put redundant information in the other ones so that you can prop it up. And so this was wound up being a really clever retrofit to squeeze every last drop of revenue out of that expensive asset that they had deployed and were constantly maintaining. Pretty clever, huh? And the design of these waveforms and how you equalize the channel is all based on transmission line theory and reflection analysis. That's what gave rise to that channel, all the reflections on that transmission line. Okay, any questions? No?